Okay, so in this video, we're going to talk about implementation of the perceptron model. So in the exercises that are associated with this video, you're going to try and implement the perceptron model yourself. So I will not be going too much into detail with how you do the full set of steps, but I'm going to explain some of the steps to you here. And then we're going to use the perceptron algorithm as coded up by Raschka, the author of the PML textbook, for classification of in a given data set, the IRIS data set. But we're getting back to that. Okay, so how can we possibly implement the different steps of the perceptron model in Python? Okay, so let's see some values of inputs and outputs. So here I'm just creating a feature matrix that has 3 observations with 2 features in it. So I'm drawing these features from a standard normal distribution. Then I also have a target vector. So that's what I have here. So the first will be a value of 1, then one of -1, and then 1 again. So positive, negative, positive classification, 3 observations as well. And then I also have 3 weights. So I have 1 weight for each of these features, and then I also have 1 associated with the bias term. So that gives me 3 weights in total. And then you can see that I draw these from a normal distribution that has been scaled here. So it's not a standard normal distribution. The standard deviation is very small. Okay. So here I'm printing the feature vector, feature matrix, the target vector, and the weights that I'm drawing. Okay, so how can we then compute the errors in a vectorized way? So in the standard implementation of the perceptron that you saw before, we will not in general compute the errors in a vectorized way, because we are looping through each observation in our dataset at a time, computing or predicting the target, evaluating whether we got the classification right or wrong. And if we got it wrong, then we would update the weights. Here, I'm showing you how you can compute all the errors basically just in one step. Okay, so how do we do that? So first we compute the net input. So that's our bias terms, bias term implicitly multiplied by 1 here, and then it's the dot product of our features and our weights, as the weights associated with the features. Okay. So that's basically matrix multiplication that we're doing. Then we are specifying that we want that we are creating a Boolean variable that we call positive, that takes a value of true whenever the net input that we had up here is strictly positive, and then it will have a value of false when the net input is weakly negative. Okay, and then we create another variable in our object here that's positive whenever our variable positive is true, and then if it's not true, then it becomes negative, then it becomes -1. Okay, so this is basically our classification, right? This is our attempt at predicting what class our given observation, the target in the observation, belongs to. Okay, and then we compute the errors here. So what we have here is basically a vector. So that's what we had before here, right? That's our target vector. And then what we have here is the classification, our prediction vector here. So that's what we have here. And so what we get is basically just a vector of errors. Okay, so now that we have computed our errors in a vectorized way, how can we then update the weights? So again, this is slightly different from a standard implementation of the perceptron, where we are looping through our dataset 1 observation of time at a time. Here I'm just presenting a way of updating the weights with a full dataset. So first I specify a learning rate, so that's eta. I set it to 0.001, so it's fairly small. And then I update the weights here. So then I say that the weight 1 and weight 2 they should be the same as before, plus eta times this product here. Okay, and then my bias term is updated with the following step here. So here I'm doing the updating in a vectorized way, and we can easily see that the higher eta is, the more do we update these weights at a time. Okay, but you're going to work much more with how you can implement the perceptron model in Python in the exercises. So I'm not going more into detail with that in this video. So we're going to play around with that yourself. So remember, if you have problems with this, just ask either me about how you do the different steps when you solve this exercise, or ask the TAs. Okay, but let's now try and use the perceptron model as implemented by Raschke in the PML textbook. So in order to illustrate how you can use this algorithm, then you should we first need a data set. So we're using the famous IRIS data set from Seaborn here. So we are loading that in the following step, and then we are only including the first 100 observations. So this IRIS data set, that's basically a data set with observations of some flowers. There are 3 different flower types in the data set, and then we have lots of different characteristics for these flowers. So what we're doing here is that we only want 2 of the flower types. That we're doing by only loading the first 100 observations. So we're implicitly dropping one of the species. Okay, so what I'm doing here now is that I'm just illustrating how the relation between petal length and sepal length, those are 2 characteristics of the flower, they are associated with the different flower species. So we can see that these 2 flower species, they are clearly linearly separable, right? When you use these 2 variables. So we can possibly apply the perceptron model to separate these 2 flower types, to classify these 2 flower types from the data set. So that's what we're going to try and do now. So what we do here is that we specify that our feature matrix, that's what the IRIS data set that we loaded up here, but then we're only using 2 of the characteristics, 2 of the features. So that's petal length and sepal length. Okay. And then we're specifying a target vector. So that's y. So that takes a value of 1 whenever we have this Setosa species in our data set. And then it takes a value of -1, so negative classification, when we have this versicolor species. Okay. So how do we then fit the perceptron model? You can load the code through that link that I provide there. But here I'm creating this classifier, so I call that CLF from the perceptron. This perceptron algorithm, this class that Raschke has coded up for us. Then I specify the number of iterations that we will make, and then I specify learning rate. And here I'm using a very, very, very small learning rate. And I'm doing that for purposes of illustration. It will be clear in a minute why it's nice when I'm illustrating how the model works that we have a small learning rate. Okay. So what I'm doing here in this step is basically that I'm fitting my model. So that you can see it requires very little code. As soon as we have this perceptron class, then we can just write CLF, so that's our classifier dot fit on our data set. And then what's going on under the hood is that the weights are updated so that hopefully we can separate these 2 flower types using these 2 different features. So how can we now evaluate our model? We can simply just print the number of errors that we obtain. That's what we do in the following here. We can see that we make no errors classifying these 2 flower types. We can also plot the decision boundaries. So that's what we have here. So what we have here is one type of flowers. What we have here is another type of flowers. And we can see that the decision boundary is such that we perfectly managed to classify these two flower categories. We perfectly managed to separate them with this decision boundary. Okay. So we may now ask, so before we can see that we specified here that we wanted to loop through all observations 20 times. How does the model performance change with the number of iterations? So that's basically what I'm plotting here. So first we can see that when we just initialize our weights, we have these random weights to begin with. We can see that we are doing a very poor job when it comes to classifying the flower types. We can see that we're making 50 mistakes, and we're making 50 mistakes because we have 100 observations, and we have 50 of each flower type. So going back to this plot here, you can maybe imagine that the decision boundary could go here, for instance. So all flowers are classified to be the same. And we can see now the first 7 times that we iterate through the whole data set, we are still classifying 50 observations wrong. But at some point, we quickly become better at classifying the flowers. Then after 20 iterations, we perfectly classify all the flowers. So you can basically imagine that this decision boundary, it slowly changes. So first it went, for instance, here, and then it became like this maybe, and then it became flat. And then at some point, we started separating the flower types. And then when we just managed to correctly classify all the flower types, we stopped. Okay, so it's this decision boundary that changes when we change the parameters or when we update the weights in our model.